In this video, I'll talk about the general linear model, or GLM. And this is basically the framework for multiple regression, where we have multiple indicators. But because everything is really so closely related, we can see that, for example, t-test is also actually a regression model, or correlation is also actually a regression model. It's a bit more general than that. The GLM is actually the umbrella term for pretty much all analysis that we're going to do in this course. It includes ANOVA as well and multiple regression. It even includes nonlinear effects in certain ways as well, even though it's a linear model. And I'll talk about that later in this course as well. Let's take a step back. Let's look again at a data set that we have been playing around with. It's just made up data, right, of animals that have some happiness score and some loneliness score. Right, and in this case, we can calculate all kinds of things, right? We know, for example, that the mean score was 15 for happiness and 14 for loneliness. We get that by summing these variables and then dividing by 10. We know that the standard deviations were 10.8 and 8.5. We get that by taking the distance from this to that, to the distance from the score to the mean, and squaring that, and then doing that for every score, then averaging that and taking the square root. And we can compute the correlation coefficient, right? And this is something that you are expected to be able to do, for example, in the exam, in this course, that you can calculate something like this by hand, right? And it takes a lot of notes, but it should be possible. So how do we calculate the correlation coefficient? We take for each score, the score minus its mean multiplied by the score minus mean in another variable. Right, so we have here 28, this owl, 28 minus 15, the mean, multiplied by 2, the loneliness score, minus the mean for loneliness, right? And that's, here we have the owl. Then we do the same for the parrot. We have, in this case here, we have 0 minus 15, the score minus its mean, and 24 minus the mean of loneliness, etc., etc., etc. We sum all these together, we get some big number, right? And minus 628. We divide it by n minus 1. We get minus 69.8. And then we can calculate the correlation as well by dividing by the product of standard deviations. That's just the formula. We get minus 0.76, so a very strong negative correlation. Now, let's do something else. Let's take the happiness score and z-transform that. So how do we z-transform? If you remember, we take a score, in this case 28. We subtract the mean, in this case 15, and we divide by the standard deviation. And just the z-score, this tells us for every data point how many standard deviations it is away from the mean. In this case, this owl is 1.2 standard deviations above the mean on happiness and minus 1.42 standard deviations below the mean on loneliness. And it's just useful because, like here, these numbers are hard to interpret, this distance, because the scale is 0 to 30. But here we can just talk about standard deviations and we can do this for every variable. And suppose now that we do a regression model where we use this z-transform loneliness score as outcome variable and the z-transform happiness score as dependent variable, as independent variable, as predictor. And we do linear regression. Now you can do this in JASP. See, this will go to 0. You can do this in JASP, and just fill in these scores and do the linear regression and try out. And then also try to compute the correlation and try to compute the significance. What happens is that the slope, how much this line goes up, one increase in z, and this is something we call a beta coefficient in this case. So we do a linear regression where we have the z-score for loneliness equals, in this case, beta 0 plus beta 1 times the z-score of happiness, the predicted value in this case. This beta coefficient is a standardized regression coefficient that is a bit more interpretable. It's between 0 and 1. And it turns out that for a simple regression, where you only one predictor, one outcome variable, that's exactly equal to the correlation coefficient. Which is really, really cool. Now try it out in JASP. Just open JASP, fill in these numbers, create 4 columns, fill in these numbers, And you just try to play around with it, do a correlation test, do a regression analysis, see that they are the same. So in this case here, I z-transformed all these scores. So the mean is 0 for both, because that's what happens after you z-transform. The line will go to 0 here. And the slope of this line, in this case minus is minus 0.761, equals this correlation coefficient, which is really cool. Right? It shows that this correlation coefficient, that this linear regression analysis are actually giving us the same result. They're telling us the same thing. And the standardized regression coefficient is something that we can interpret. For one predictor, it's a correlation. For multiple predictions, no longer correlation, but it's still between 0 and 1. Now let's say I have loneliness not measured as a continuous variable, but let's say I have measured it in different groups. I just have not lonely or lonely. And suppose I say that not lonely is 0 and lonely is 1, which is what we call a dummy encoding. Okay. We can calculate the mean between these two groups. We can say the mean for the non-lonely animals, the ones that are encoded as 0. Right? We just take the happiness score of this one, this one, this one, this one, and this one. We add them, divide them by 10. We get 21, or not 10, sorry. 1, 2, 3, 4, 5 in this case. We get 21.4. The mean score of happiness, we get 8.6. We get two means, but yeah, are those significantly different from each other? We don't know, but they are different, of course. It's a sample. We don't know if they are significantly different from each other. How do we test that? Well, a t-test, normally, right? Because you have two groups. But in this case, I encoded them as 0 and 1. And I'm going to do something really weird. I'm going to actually do a regression analysis instead. So the regression looks like this. Now, because this is 0 and 1, I can put this in a graph, in a line. I can, the numbers, right? I can multiply things with numbers, I can add things, etc. So here I have my line. Yeah. I have the not lonely group, and I have the lonely group. And basically all these are at the same place. And all these are at the same place. We see that this group with lonely animals is lower on happiness than this group with non-lonely animals. It turns out the line at this point, so this line is really only relevant at exactly this point and exactly this point, right? There's nothing really here that's interesting. Right, so this is the point where this line is relevant in this case. Turns out that the point where this line crosses these points is exactly the means of these samples. And what is the interpretation? What's the interpretation of the intercept? Well, this is 0, right? So the point where the x value is 0, right? That is the height of the line for one group, so that's the mean of the group. What's the interpretation of the slope? That's the increase or decrease with a 1 unit increase in x. 1 is from 0 to 1. So that means it's exactly the same as the difference between the two groups. Now, if this is 0, it's equals to 0, and that means the group have an equal mean. If it's not equal to 0, it means the group cannot have an equal mean. And it turns out that if you test for the significance of this B1 parameter, then it's actually the same as testing as doing a t-test, which is really cool. Here in an example, I just put this data. I used R, which is a programming language that you can use for statistical tests, but you can try to replicate this also in JASP. So I do a t-test, independent samples t-test or two sample t-test. I assume homogeneity invariance, and I get t equals minus 2.255 with 8 degrees of freedom. Why 8? 10 minus 2, that's the rule, and minus 2 in this case, because you have two parameters, right, intercept and slope. You get a p-value of 0.5414. Here do linear regression. This is what the output looks like in R. In JASP it looks a bit different, but basically this table is the same. And that's because JASP actually just uses R in the background. It does actually this. So what do we get? We get some intercept. We're not interested in that, but we're interested in this one here. This not lonely one. we get a t-value of 2.255 and a p-value of 0.0541. The same. Minus 2.255, 2.2.555, well that doesn't really matter, that's basically how it's encoded. P-value 0.054, p-value 0.054. It's the same value. We get here our 8 degrees of freedom. This is the thing we're looking for, the t-value. But look at that, what does this say here at the bottom? Some other stuff here. Residual standard error, 8.975 on 8 degrees of freedom. That's what actually leads to degrees of freedom in the t-test. But we get this thing, we get the r squared, which is our explained variance. And we get some test here. What is this test telling us? An F statistic is not a t statistic, it's an F statistic. But the p-value is exactly the same. Wow. But this is doing something different. And this is what we'll learn about later in the course. The F test is a test that we use to compare this model to a null model. In this case, a model where we don't have a predictor. But since there's only one predictor, the result is actually the same here. Yes. Here we have the correlation in R. Again, it will look different in JASP. But we get a t-value of minus 2.255, degrees of freedom of 8, and p-value of 0.5414. It's the same. Right? All these things are doing the same thing, which is really cool. And it shows that we can actually interpret everything as a regression model. And this is why we talk so much about regression in this course. And yeah, the regression is such an important topic here. That is why in field, the book actually has only chapters GLM1, GLM2, etc. Because everything is the linear model, everything is a regression. So most things we do in this course can be considered a linear regression model or general linear model. This general linear model is a term for the general multivariate framework that encompasses all these models. Right? So field actually mentioned GLM1, GLM2, GLM3. That's because it's all GLM. The univariate GLM variant is a multiple regression model with multiple predictors. So univariate here means that the outcome variable or the dependent variable is one variable. And we always talk about one outcome variable in this course. You could actually make it even bigger. And then we're talking about having multiple variables as outcome variables. That's also included in the GLM model. And then we can do tests to see if like people differ at the same time on 3 different variables. When we only have one dependent variable, we talk about univariate GLM. In this case, GLM is actually the same as a multiple regression model. So we talk about a multiple regression model. Multiple regression model means that we have multiple predictors. So far we talked about one predictor, B0, an intercept plus one predictor here, right? One linear predictor, that's loneliness, for example. But now we add more predictors, and dot to dot here means as many as we want. K predictors. It could be any number. So maybe we have 3 or 4 or 5 predictors. And the formula looks like this, like we have B0, the intercept, plus one slope corresponding to one variable, plus another slope corresponding to another variable, etc., etc., etc. Or the sum of all these regression coefficients times the predictor. And these predictors can actually just take several forms, as we saw. They can be continuous variables, normally distributed, but they don't have to be. They can be dummy variables, 0, 1, or even, like, for example, some transformation of variables, like maybe we multiply 2 variables together, or we square a variable to get a nonlinear effect. You can put anything we want really is there. Like any column that you might have in your data, you might get in your data, you could put in as a predictor in your model. And that's what we will see a lot. Right, so here I have an example of a multiple regression. So now I have happiness, loneliness, and let's say I add 2 more predictors, age, and if you're taking a stats course or not. Yeah. Dummy encoded here 0, 1. Could be yes or no, for example. Right, so maybe we have these animals. Well, they're all very old animals. I just generated this data. I don't actually think many of these animals live to be 32 years. A hamster living 32 years would be nice, but unfortunately that's not the case. And my little niece's hamster Cookie passed away last year after only a few years. But this hamster in this fictional data set lives to be 32. That's nice. But anyway, we have hamster, we have loneliness, and we have stats. Are you taking stat scores or not? So maybe we're instantly seeing, okay, which of these things is predicting happiness, and which of these things is predicting happiness the most, which are important for predicting happiness. Right, so is happiness predicted by loneliness, or maybe also age or stats? Right, and what we can do with this analysis, so we can already do a correlation, right, for each of these, or a linear regression, simple linear regression for each of these, right? Why are we doing this? Is now we can see, okay, does age predict happiness more than loneliness does, or beyond what we already know from loneliness, for example. So here we have our multiple regression model. We have our intercept. We have one slope for loneliness, one slope for age, and one slope for taking stat scores. And also in this case, encoded as 0, 1. That's a grouping variable. So we have P equals 1, 2, 3, 4. Oh, that's a 5. Oh. 4 parameters. Yeah. So this model, if we estimate the parameters from data, right? So we get a height of the line and we get estimated parameters from data. We get a predictive vector, height of the line, which in this case is B0 plus B1 times loneliness plus B2 times age plus B3 times stats. Now, I say height of the line, technically it is a line, but it is some sort of hyperdimensional line that we can't really picture anymore. And that's a weird thing about this here, right? With one variable, we can put, let's say, loneliness here on the x-axis, right? With two variables, so you can see there's a 3D plot with maybe age here. With three variables, yeah, we can't, like this is happiness. With three variables, we don't have like 4 dimensions, so it becomes harder to visualize. And we can only really look at the numbers and not really at the model itself or the picture. So this model has 3 predictors, loneliness, age, and stat scores, and because of that, 4 parameters, B0, B0, B1, B2, and B3. Right, so what does this look like? Well, I said it's hard to visualize in 4 dimensions. We can still do it in this case, because we have one grouping variable. We have happiness, and the predictors are loneliness, age, and the grouping variable. So a different line between stats, the subjects that take stat courses, and the subjects that do not, in this case. So we can see now our linear model, it's actually it's no longer a line, really. It's more like a plane, like a surface, right? A bit hard to interpret, but for each of these points, you can calculate a predicted value. As in this case here, if you have a 25 on loneliness and a 25 on age, you would be basically in this point, you would predict to be somewhere here in this line. It's hard to see because it's a 2-dimensional screen, of course, right? And then, of course, also if you have no stat scores. All right. So now, I did something even more crazy. This is already weird. We had 1, 2, 3, 4 parameters, and now I add a 5th one. I add a 5th one, which is the regression coefficient that corresponds to an interaction effect between stats and loneliness. Whoa, that's weird, right? But basically we have here 2 columns that are multiplying with each other, and we can add it as another predictor in the model, and we can really make it as complicated as we want it to be. We can put as many predictors in there as we want it to be, and we're not going to really go on beyond like 4 predictors on the scores, but yeah, that's the idea. Multiple regression can be as big as you want it to be. You can put age in there, stats, but also age times stats, for example, or some interaction effect, and that's what we will see later as well. Right, that's it for this video.